Welcome back, stats friends. We're here. This should be, if everything's going to plan, this should be the last lesson for our first semester. Woo! All right, which makes a lot more sense because when we stopped at chapter 5, that was too soon. All right, so this final lesson, we're going to talk about some very large topics in this chapter, the binomial and eventually the geometric random variables and their distributions. So, lots of activities coming up in this series of lessons. This is going to take us like 3 days just to present the material, and that doesn't include all the other fun stuff we do. So hang tight. I'll try to remember to tell you where the breakdowns are. I actually wrote that down somewhere. I should look at that before we get going. Okay, we'll see if I can remember. Day one's going to end with us calculating binomial probabilities. So heads up if that's what you're looking for. All right, so we have binomial settings and a binomial random variable. So a binomial setting arises when we perform a certain number of independent trials, they call it n, of the same chance process, and we count the number of times that a particular outcome occurs. We call those successes. And of course, you might think, okay, what do we call the other things? Well, we call them failures because that's what we do in math. So there's 4 conditions that we have to satisfy before we can determine whether a binomial random variable is what we're looking at. So the first thing we have to find out is it binary? Binary meaning there's only 2 outcomes. Anytime something happens, you either call it a success or a failure. There can't be any other outcome possibility. Are the trials independent of one another? So knowing one outcome of the first trial has nothing to do with what's going to happen on the second trial. We've talked about this a lot with the coin toss before. A lot of kids feel like just because I just flipped the coin and it landed on heads that the next one's more likely to be tails. Well, we know that's just not true. These are independent events. So the number of trials is fixed. I know ahead of time how many trials that we're going to have, and that the same probability occurs with each individual trial. So the probabilities don't change, and that kind of goes along with the independence. So the cute acronym that we come up with is BINS. Check your BINS. That's what we say. So is it binary, independent? Can you identify the number in advance, and do they all have the same probability? So every time we go to determine whether we can use a binomial distribution, we have to ask ourselves those 4 questions. So first here we have some problems, and we're going to decide whether or not this is a binomial setting, and then we're going to explain why or why not. So genetics say that the genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. So B, is it binary? And the answer is yes, because we would be calling type O blood as being a success for this setting, and then not having type O blood as a failure. I know there's other types of blood, but all we're measuring here is it type O or is it not? Is it independent? Yes, we already know, and we were told specifically in this problem that the genes that you receive from your parents, that's independent from one child to the next. The number, we know ahead of time that there's 5 children we're looking at, so that's the fixed number. And then is it a fixed probability? Yes, every single child has a 25% chance of having type O blood. So this is indeed a binomial setting. So as far as justifying your answer, you have to go through BINS. Yeah, you gotta say all of them. So here we're shuffling a deck of 52 playing cards. We turn over the first 10 cards one at a time and record the number of aces that you observe. So is this a binary setting? So success and failure would be getting an ace versus not getting an ace. So it is this setting is binary. Are the events independent? Well, in this case, the answer is no. So we're going to stop doing BINS, obviously, because we found out no. But if the first card is an ace, that means the next card has a different probability of becoming an ace because we're not putting the card back into the deck. They're sitting out on the table. So like the first time you flip over, you have hello, Abruzzo, 4 out of 52 chance to have an ace. And if it was an ace, the next time you have a 3 out of 52 chance. So it changes the probability. So not independent, and therefore this is not a binomial setting because the independence condition is not met. That's the rest of that sentence. All right, so here we're shuffling a deck of cards, turn over the top card, put the card back into the deck, shuffle again, and keep doing it. and then do it until you get an ace. So they've taken away that independence issue because they keep putting the card back into the deck. They replace it. But you notice there's no ending number. We don't know when this little experiment is going to stop because we're just going to keep going until we get an ace. It could be the first time, second time, third time. We might have to wait till the 48th time. I don't know. There's no fixed number of trials. This is not a binomial setting. All right, so let's take a look at some example here that is a binomial setting, that blood type question. So we'll let x equal the number of children with blood type O. And x is a binomial random variable. We've determined that because we checked our bins. The probability distribution of x is called a binomial distribution. Thank you, stats, for naming things what they are. That's nice. The count of successes, which x is what we call them in a binomial setting, is the binomial random variable. Notice capital X. The possible values of x are 0, 1, and then it goes on until you hit the number n. So like for our blood type question, there could be 0 children with blood type O, 1 or 2 or 3 or 4, all the way up to 5. That's where it ended. The probability distribution of x is a binomial distribution. We talked about that. Any binomial distribution is completely specified by two numbers, the number of trials, which we call n, and the chance process and the probability p of success. So as long as you know number of trials and probability p, that's how we're going to be calculating the binomial probabilities and eventually the distributions. So we're back to our deck of playing cards. What are we supposed to do? Oh, this is to check your understanding. So is it a binomial setting? In a moment, we're going to have you pause the video and write down some thoughts. So the first question is, we're shuffling a deck of cards. Turn over the top card, put the card back into the deck, shuffle again. Repeat this process 10 times, and let X be the number of aces that you observe. So number 2 is going to be choose 5 students at random from your class. Let Y be the number who are over 6 feet tall. And number 3, roll a fair die 100 times. Sometime during the 100 rolls, one corner of the die chips off. Let W equal the number of 5s you roll. So pause the video and go ahead and decide whether these are binomial settings, and you're going to check your bins. All right, answers coming your way. So that first deck of cards question, where they shuffled, turn over the top card, put them back in, shuffle again, do it 10 times, and then observe how many aces you get. So it is binary because you're either getting an ace or not. So that's the success and failure idea. They are independent because we're placing them back in and shuffling. And shuffling is an important part. Sometimes kids forget that. It's not just about replacement with a deck of cards. You got to shuffle too. The result of one trial does not tell you anything about the outcome of the other, so there's another way to think about independence. We do have a fixed number. It was 10. And each time we pull a card, we have the same probability of getting an ace, which is 4 out of 52. So with all that good stuff, this is a binomial setting. So his distribution would be an n of 10 and a probability of success of 4 over 52. Don't bother reducing or changing it to anything like a decimal. Just write down what you see for these. I'll be honest, we're going to be using our calculator a lot, and you know your calculator doesn't care if we reduce. So the second question, which I already forgot what it was, 5 students from your class, figure out who's over 6 feet tall. So it is binary. Success is being over 6 feet tall, and failure is not over 6 feet tall. And is it independent? Because we're selecting without replacement from a small number of students, the observations are not independent. Keep going. Number n equals 5, we did have that. Are they the same probability? The unconditional probability of success will not change from trial to trial, but because the trials are not independent, this is not a binomial setting, so we don't have to continue on and figure that out. That one's kind of harder for kids to understand. Because we don't usually think about people as being replaced, because that just sounds weird. But when you only have a small number that you're sampling, and you're like looking at one and then the other and then the other, they are no longer independent. They're not. I don't know a better way to say that one. I think we need to talk about that one in class a little bit more. That's harder to explain without an audience, I suppose. My bad. Okay, number 3, forgot what it was. We're rolling a fair die, and then at some point the corner chips off. So it is binary because it's either a 5 or it's not. Independent. Because you're rolling a die, the outcome of any one trial does not tell you the outcome of the other trial. So that we know. They don't have anything to do with each other. It's a fixed number of 100 trials, but because the corner chipped off, the probability for each outcome is going to change a little bit. And they didn't really tell us specifically where it chipped off, but it's going to change how the die rolls and whether it will sit nice and flat on a side or be more likely to tip to the other side. So it's not what we call a fair die anymore, and therefore we can't use a binomial setting. Okay, calculating binomial probabilities. Here goes. Now, full disclosure, we're going to show you the long way to do this by hand. And these formulas you're about to be exposed to are definitely on your AP formula sheet that we will have access to all the time. But we're also going to do this on the calculator. And of course, we're going to teach you both ways and we're going to practice it both ways. But when it comes to crunch time, studying for the test, you're going to see me kind of deviate to my calculator quite a bit. All right. Each child of those parents, remember, have a 25% chance of having type O blood. Suppose these parents have 5 children. So that same example from before, which we've already determined to be a binomial setting. So what's the probability that exactly one of the 5 children has type O blood? Well, one way to think about that is using the formula, which we haven't shown you yet. They're just kind of throwing it at you here. The probability of having exactly one child with type O blood. Well, the first thing they'd have to do is multiply how many ways you could get one child out of 5 with type O blood. And, we can do this the long way where we have like child A, B, C, D, E, and then kind of go through like A could have type O blood or B could have type O blood, C. And then we'd find out pretty quick, well, there's only 5 ways for that to happen. So that's a pretty obvious way of how they get 5. We'll talk about where that number comes from in a moment because they're not so obvious sometimes. And then what we're going to do here is that, remember, one kid has type O blood. So the 25% success is for one child, but then those other 4 children are going to, quote, fail. So the probability of failing this is having not type O blood. So 75% times 75% times 75% times 75%, so that's to the 4th power. And the answer comes out to 0.3955. So that's the probability of one of their children having type O blood. Okay. So here's the formula. This is not what it looks like on the formula sheet, but this is the nice explicit formula in words. Number of ways to get k successes in n trials. We'll learn in a minute. It's called a binomial coefficient. It's a combination problem. Success of probability to the kth power, and then fails n minus k. So you'll notice these kind of have like a complement idea to it. All right, here's the formula that you'll be seeing. Or no, it's not. I lied. This is just the formula for what's called a binomial coefficient. This is the notation that's used often in stats. When you have a parenthesis set and there's like a number stacked on top of another number, this is the formula. These are called factorials. So n factorial means you'd start with whatever number n is, the total number of trials, and you multiply it by every integer all the way down. And we'll do a better job in class of showing you what this means. So if it was like 5 factorial, it would be 5 times 4 times 3 times 2 times 1. And then k, remember, was successes, how many successes you're going to have. So like in our example, it was just a 1. So 1 factorial is just 1. And then n minus k, well, that in our example was 5 minus 1, so that'd be 4 factorial. So that would be 4 times 3 times 2 times 1. These formulas are kind of interesting because at first you're like, oh my gosh, I got to do this by hand. Well, no, of course not. But even if you did, they're not too bad because a lot of stuff cancels if you had to do it by hand, which we'll show you in class again. Turns out we're not going to really make you hand calculate this in our class either, but it's fun to know. Oh, a little side note, if you ever see a 0 factorial, that's just a 1 because you don't want to include a 0 into this formula. Now, a lot of kids at first glance, if they have no idea what this notation means, they think it's a fraction. It has nothing to do with a fraction, so watch out on that. So I mentioned that this is known as a combination. So in probability, we would talk a lot about combinations and permutations if you were taking a straight probability course, maybe later in college. So a combination is, choosing things from a larger number. So how many teams can you create? So in our case of that blood problem, how many ways can we um, assign that one blood type to one of the 5 children? So this example here, it's 5 choose 2 is the way we read that. And you can find the combination command in the math menu. And then you go over to probability and you choose the one that says NCR. Now, in our older calculators, you'd have to type the 5, then pull up the command, and then type a 2. In our newer calculators, you can just go into the little edit boxes and put the 5 and 2 as you see fit. And that's in place of using this formula here, because nobody likes that formula. Not even your teacher, so that should tell you something. Okay, so here is the actual probability calculation. So if you're trying to find in a binomial probability question, the probability of having an exact number of successes, what you do is you first multiply by what we know is a combination, that binomial coefficient, and then successes to the k power, and then failures to the rest. So that's kind of the simple way to think of it. Again, this is on your formula sheet. So if you are in a jam and you're later on, trying to do this and you can't remember how to do anything on your calculator, you could figure it out this way. It's not great. It'll take you a minute, but at least you'll have a lot of work to show. All right, so let's look at this question again, the blood type question. We already talked about one child. Let's do the same question, but this time having exactly 3 children with type O blood, and then interpret what that answer is. So they kind of halfway cheated, if you want to think of it that way. They partially used their calculator, but the first important thing was to set up everything, all the parameters. So n is 5, because remember there's 5 children, and then the probability of success having type O blood is 0.25, and we're wondering about the number 3. So k in this problem is 3. So n choose k, so 5 choose 3, which they chose the calculator to figure that out. So they didn't want to use that icky n factorial problem. I don't blame them at all. So that's where this 10 is coming from. And then how many successes were we going to have in this problem? 3 successes, which means how many failures? That means we have 2. Straight up using the formula, remember it was k power here and it was n minus k. So 5 minus 3 is 2. I always think of it in terms of being complements to each other. That's the nice thing about binomial distributions is it's either this or it's this. It's a success or it's a fail. You either are or you aren't. So it's pretty easy for our brain to do some of that math. Crank that in the calculator and you get this, which is roughly 8.8%. So for our interpretation here, there's about an 8.8% chance that exactly 3 of the 5 children have type O blood. That's how we interpret that. All right, same question, but now they're going to change it and say, suppose the parents have 5 children. Should the parents be surprised if more than 3 of their children have type O blood? Well, more than 3 for us, now notice there's not a or equal to situation here. It's more than 3. So that means 4 children or 5 children. So would this be surprising to have? Let's find the probability. So what you're going to do is you're going to find the probability of 5 choose 4. I think there's a mistake here. This is supposed to be 5 choose 5. I don't know what happened there. I'll have to fix that slide. All right. So what's going to happen is we're going to fix this later, I guess. Sorry about that. 4 successes would be 5 choose 4. Remember, that's a combination on a calculator. Success 4 times, failure 1 time. And then over here, 5 choose 5. Success 5 times, failure 0 times. This is what the decimal should come out to. I don't have a calculator on this computer, otherwise I would show you that other one fixed. And then when we add them together, we get this decimal, which is approximately 1.5%, 1.6%. So because there's only a 1.6% probability of having more than 3 children with type O blood, the parent should definitely be surprised if that happens. That is very unlikely to happen. So that would be an anomaly. But possible. That's the thing about stats. All right. So I kind of alluded to this earlier, and remember, I don't really love formulas. If I have a technological approach, I'm probably going to use it. But remember, the catch is when we go to an AP exam answering a question, we can crank stuff in our calculator all we want, but we got to make sure that we tell our reader what we did very specifically. So to compute binomial probabilities on the 83 or 84, the TI 83 or 84, we're going to go to the distribution menu, and there's two options that look like they're possibilities. There's Binomial Pdf, and there's also Binomial Cdf. So if you are wanting to know exactly at a certain number of successes, like the example where it said having exactly 3 children that had the blood type of O, you would choose Binomial Pdf. Now on the older calculators, you're going to have to remember that it goes in this order. Number of trials, comma, probability of success, comma, number of successes. And then it'll give you that same probability that you were calculating with that weird factorial formula with the successes and failures, or something very comparable, if not exactly the same. The other question, however, where it was like greater than 3, well, your binomial distributions, if you pull up Binomial Cdf on your calculator, this represents the cumulative distribution frequency. So it kind of, think back to your normal distribution. When you were in your book and you were reading about probability on the curve, remember how it measured to the left? So it always measures less than. So when they type in binomial CDF of 5, 0.25, 3, they're getting the probability of 3, 2, 1, 0 because it's measuring down the curve. Well, they wanted the other side of the curve. So they just do 1 minus that probability, and that gives them everything less than or, greater than or, no, just greater than 3. Now remember, the equal to bar makes a difference. So whatever number you're putting here for your K, it's going to count it and everything to the left of it. So essentially it's a less than or equal to question when you're measuring on a binomial CDF. So when they just found binomial CDF measuring to the left of 3 and to the left, they got 0.984375, obviously a very large probability, but when they found the complement to that, they got that tiny probability that we were looking for. I'm forgetting right now, but I think the answer is yes. I think on our newer calculators, it asks you whether it's left or right, but let me check that. I do have one on my phone. I'm going to cheat for a moment. Oh, that's not my right app. Hold on. Oh, maybe not. I lied. I'm thinking of something else. That would have been cool. It does not give us a choice. Darn. Okay, so on the newer calculators, it's going to have that cool paste menu where it says, trials, P, and X value, and then you paste it into the formula. That's why we love using our TI-84CEs, because the guided window, the guided menu is so nice for people like me who just can't remember anything. So here's your warning about your using your calculator on the AP exam. They will not accept calculator speak. So if you just write down what you cranked in the calculator, even with an interpretation, they're not going to give you any like a full credit. So you have to say this. So that's why those nicer, newer calculators are really worth it, because trials, they were 5, the p-value is 0.25, and then the x value is 3. If you wrote words out rather than binomial, PDF, blah, 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 other than like these words, as long as they were the same meaning, it would be fine. So just make sure that we're answering very explicitly with our calculator, that we actually know what we've typed in our calculator. That's what they're trying to find out. So how to find binomial probabilities. First, state the distribution and the values of interest. Specify a binomial distribution with a number of trials, n, success probability, p, and the values of the variable clearly defined. Then we're going to perform the calculations showing work. So whether we use the formula with the factorials and all that good stuff, or whether we use a binomial PDF CDF command in our calculator, as long as we've done a good job of labeling and showing our work, we're going to get our credit. And then of course we have to actually answer the question. Don't forget that part. All right, so a local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders a touchscreen display, a touchscreen display shows a message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. On the first day of the promotion, 250 customers place lunch orders. Find the probability that fewer than 10 of them win a free lunch. So, we didn't have to go through with like proving this is binomial, but we could have gone through bins to make sure that we understand it is a binomial setting. So what they're going to say here is we have to first remember, go back to this list here, Bruzo. Boop, boop, boop. We have to state the distribution and the values of interest, and then specify the n, the p, and then the variables. So there we go. So y is the number of customers who win a free lunch, because we have to use some sort of a variable here. Y has a binomial distribution, so we notated it was binomial with, and then here comes the good information, n of 250 and p of 4 over 25, because they want to know probability of drawing a 3 in a standard deck of playing cards. That would be 4 out of the 52. So the probability that y is less than 10, well, you could do a couple of different things. I need to fix this. I'll have to remember to fix that too. Gosh, lots of typos that I didn't catch. My bad. This is supposed to be a 9 here. So they've gone ahead and used the calculator's Binomial Cdf because they want to have the cumulative distribution. But remember, it's going to measure from this point down. So if we say like 10 for the x value, it would have counted 10, 9, 8, 7, 6. Okay, we don't want the 10th one. So that's why they changed the x value to 9. I need to change this to a 9. So everyone scribble that out and make it a 9. So the binomial CDF trials, no one's house labeled, trials of 250, P of 4 out of 52, and then 9 is what they're measuring up to. Small probability, 0.6%, which they didn't actually make us write a sentence out, so that's okay. But I think we should notate in our head, like the probability, what was this again? Fewer than 10 win a free lunch. That's a pretty small probability by chance. In fact, only 9 customers won a free lunch. Does this result give convincing evidence that the computer program is flawed? Yeah. There's a tiny, tiny probability that fewer than 10 would receive a free lunch, and they got 9, which is obviously fewer than 10. So I'm thinking the computer program is either not working properly or possibly it's rigged on purpose because they don't want to give out free lunches. But I don't know that anyone's going to attack them for that because it's free lunch. All right, so we do have convincing evidence that the program is flawed. Its probabilities are not quite working out right. All right, to introduce his class to binomial distributions, Mr. Miller does a pop quiz activity at the beginning of this section, which, oh, geez, another thing I forgot to do. We had to go to page 431. All right, each student guesses an answer A through E on each of 10 multiple choice questions. Mr. Miller determines the correct answer for each of the 10 questions randomly so that A, B, C, D, and E are equally likely to be chosen. I know you guys think we put a lot of thought into like, oh, the next one is going to be B, the next one's going to be E. No, we usually don't. Hannah is one of the students in this class. Let X equal the number of questions that Hannah answers correctly. So what probability distribution does X have? Justify your answer. Use the binomial probability formula to find the probability that X is exactly equal to 3. Interpret this result. And to get a passing score in the quiz, a student must answer at least 6 questions correctly. Would you be surprised if Hannah earned a passing score? Okay. So we are, let's see, do you have all the information you need to freeze? I think so. All right. Pause, write down some thoughts. All right. So, back here. That when they went to go, of course, I stole the answers from the book because I don't want to retype everything. When they go to set up the, what probability distribution does X have, justify your answer, they did go through the fact that it's binary because you have success and failure, answered it correctly or did not. It is independent because Mr. Miller randomly determined the correct answers. So if you know the number 1 is B, it doesn't mean the second one is not going to be B. There's a fixed number of 10, and they all have the same probability of 0.2. If you're wondering why the 0.2, it's because there's 5 choices, right? So 1 out of 5 is 20%. So this is a binomial setting, and then here's their defining it. So X has a binomial distribution with n equals 10 and the probability of success of 0.2. So then in question 2, to find the probability of exactly 3, you could have used a binomial Pdf on your calculator where you used 10, comma, 0.2, comma, 3, and you would have come up with an answer very close to this. They chose the old school formula with the combination here in front, 10 choose 3. You get it right 3 times and you get them wrong 7 times because remember there's 10 questions. And then to interpret that, there's a 20% chance that Hannah will answer exactly 3 questions correctly. So that was a binomial Pdf if you did it on your calculator. Now the other question is about passing. So they're saying in order to pass it, you have to get at least 6 questions right. So we want to find the probability that someone gets at least 6 questions right. Well, remember your curve measures from this point down. So we don't want 6 and down. What we actually want is 5 and down, and then we want to find the complement to it. So the first thing we're going to do is find the probability. I mean, you could technically do this in one step on your calculator, but I usually don't. Find the probability that x is less than or equal to 5, which is 0.9936, and then find the complement to it. So 1 minus that is 0.0064. So a 0.6% chance that someone passes this test. Ooh, Hannah, that's not looking good. I think Mr. Miller needs to revise his quiz, man. Well, let me rephrase that. This is just if Hannah's guessing. Oops. If Hannah's just guessing on a 10-question quiz on every single question, Hannah probably doesn't deserve to pass. I take that back. Mr. Miller, you do you. You're doing good. All right. So that's kind of a cool idea for binomial. Sometimes kids are like, "Oh, what's the likelihood that, I could pass this if I just randomly guessed on everything?" I don't know how many of you have heard this from a kid. "Oh, I know somebody who just drew a random design on their SAT and they got a good score." It's incredibly unlikely that that happens. So, I usually just ignore that when some weird child tells me that. All right. I think for sure we are, oh man, guys, I forgot to tell you where we stopped day 1. I think I told you at the beginning of the lesson and then I forgot to acknowledge it. So actually, nope, we're good. This is the start of day 2. So day 1 is a hoot. I'm going to be honest, when we're teaching it live, I think I'm going to show you guys that one formula like one time, and then we're pretty much going to do the calculator from there out. Those of you who are in pre-calc, you do the binomial distribution, the probabilities, later on in the year. And if you had pre-calc last year, maybe this is familiar to you. Or not. Maybe you guys didn't do it last year. I'm not sure. It's one of those cool topics that Mrs. Hoffbauer or sometimes me, we like to teach, but if we don't get to it, it's not the end of the world. For stats, yeah, we got to learn it. So here we have a table, shows the possible values and corresponding probabilities for X, which is the number of children with type O blood again. Remember, we have 5 children in this family with a probability of success of 0.25. So what they've done is they've found those exact probabilities for each of the outcomes. So the 0.2370. And by the way, remind me in class to show you, like you can come up with this distribution by just doing your binomial Pdf and not put anything in for the last number. So what does your calculator call them on the new one? Hold on. The X value, just leave it blank. And then when you go to paste it, it'll give you the entire distribution out all by itself. So that's pretty nice. Obviously, you don't want to do that if you have a lot of n. Okay, so here's the probabilities. You can see where the bulk of them lie, over in this area. So this probability distribution is skewed. So it is skewed to the right, which makes sense. The probability of having type O blood is fairly small. So you shouldn't have a high probability with all 5 kids having that type of blood. That's just not how math works. That's not how probability works. So just like all of our other distributions, they can be skewed, they can be symmetrical. Here's a little blurb, and remember you can watch this video for more detail in your book. You can go on your online book, obviously. We can graph the distribution. What we're going to do is we're going to put our outcomes, our possible outcomes here. So we could have 0 successes all the way down to 5 successes. And then to get this to fill out, this is what I was kind of talking about earlier. You can make the distribution values kind of paste into a list. So what you do is you put your cursor up in L2, and then while you're hovering in L2, you're going to enter the command Binomial Pdf 5, comma 0.25, and notice we don't put anything at the end. So for X value, we just leave it blank if you have the paste option. And then when you hit enter, it's going to like whoop, fill everything in. It's going to give the whole distribution in order. So that's pretty nice. Then when we go to make the histogram, we're just going to graph it by going to changing our plot, into a histogram. And we're going to adjust the window so it makes sense, of course. And there you go. So remember, this is 0, 1, 2, 3, 4, 5. So if your window's weird when you hit stat plot, you want to make sure your X is changed to that. Okie dokie artichokes. So if you don't want to draw it by hand, I don't blame you. I mean, they're not horrible to draw by hand, but you know me, I love my calculator. So this particular distribution of X, which is a totally different distribution than the blood type problem, looks fairly symmetric. Okay, so it has n value of 5, a p-value of 0.51. This one, however, notice how the p-value success probability is higher, so you're going to have a cluster of data up yonder. This one's skewed to the left. So if a count, now we're going to talk about mean and standard deviation of these distributions. So here goes. If a count X of successes has a binomial distribution with number of trials n and probability of success p, so all the same stuff we've been talking about, you can find an expected value by simply multiplying n times p together. So number of trials times the probability of success. Simple enough, right? Well, of course, their standard deviation is going to be weird because that's not as easily calculated. The standard deviation for that distribution is the square root of n times p, so that expected value, times failure. So 1 minus p, remember, is the probability of failure. These are on your formula sheet. These only work for binomial distributions. So before you start throwing down a bunch of work, you want to make sure that you have the right kind of distribution. So you want to, whether it's mentally or literally, go through the bins before you determine if you have binomial. Assume that each of the 21 students in Mr. Hogarth's AP Stats class who did the bottled water versus tap water activity was just guessing. So there's a third chance of each student identifying the cup containing bottled water correctly. So this is an activity that's displayed in our book, and we'll look closer at it in the class. So let X equal the number of students who make a correct identification. At the right is a histogram of probability distribution of X. Calculate and interpret the mean. So remember, is it binomial? We'd have to go through the bins, but this one is. They're just kind of telling you. Calculate the expected value, the mean. So that would be n times p. So if there's 21 trials and they were just guessing, so they have a third of a chance of winning in this example. So 21 times 3 is 7. So the way we interpret that mean is that if all of the students in the class were just guessing and then we repeated this activity many, many times, the average number of students who correctly guess would be about 7. Okay, lots of not clear statements there, but that's stats for you. Now we're going to do the same thing for standard deviation. So the standard deviation formula was the square root of n, 21, times p, 1/3, times failure, which is 2/3. Calculating that to be 2.13. So now to interpret that, if all the students in the class were just guessing and we repeated this activity many times, the number of students who guessed correctly would typically vary by 2.16 from the mean of 7. There's that formula for how to interpret standard deviation. I'm sure you've seen that show up so many times throughout the semester that, again, we talk about, having a template so we can answer these a little easier. Anytime you have to interpret standard deviation, you kind of follow that same pattern. To introduce his class to a binomial distribution, I love this question. Mr. Miller does a pop quiz activity at the beginning of each section. Each student class, wait, didn't we do this one? Oh no, a little different. Okay. That poor Hannah, she's back. All right. So it's that same 10-question quiz. Mr. Miller determines the correct answer for each of the 10 questions randomly, so same as before, so it is binomial. Hannah is one of the students in the class. Let y be the number of guesses that Hannah answers incorrectly. All right, so this is a little different than the previous question. Now we're doing the distribution for being incorrect. So first we're going to use technology to make a histogram for the probability distribution. Now this is confusing because your probability of success on this is getting something incorrect. Keep that in mind. Calculate and interpret the mean, calculate and interpret the standard deviation, and then you can go back to your book if you want to look, but it does reference back to that page. We defined X to be the number of correct answers that Hannah got on a quiz. How do the shape, center, and variability of the probability distribution compare to what we just got on the other distribution where we are answering incorrectly? So pause the video, try some things, definitely make that distribution on your calculator. All right, so if you were to do the probability distribution on your calculator, and I probably should have put in another slide here, what you had to do was in list 1, put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's in list 1. And then in list 2, you go up to the name where list 2 is, and we would do Binomial Pdf, and it was 10 trials. But remember, this time probability of success is getting it wrong. So it's 0.8 is the probability of success. So you'd put a 0.8 for the P, and then you would leave the X or the trials part blank. Don't put anything. And then once you had those into list 1 and list 2, you would go graph your histogram, and you would see this, which is definitely left skewed. We'll talk about that in a moment. So the next question was interpret and find the mean and find and then interpret the mean and the standard deviation. So the mean, which is just n times p, is 8. So the interpretation of that, if many students took the quiz, the average number of questions the students would answer incorrectly is 8 questions. If they were just guessing, I guess. Standard deviation would be the square root of n times p and then times the failure. Well, that's confusing because failure is getting it right this time, but whatever. All right, square root of n times p times, a lot of books call this q. If you ever take another class in stats, they might call this guy q instead of 1 minus p. That comes out to 1.265. So the interpretation of that is if many students took the quiz, we would expect individual student scores to typically vary by 1.265 incorrect answers from the mean of 8 incorrect answers. Notice the context there of being incorrect answers. My pea brain would forget that these were incorrect answers, so good thing they did kind of determine that on their histogram at the beginning. Now, I don't have a picture of this, but the distribution of the original X variable was skewed to the right, remember, because the probability of getting a question right was small, right? 0.2. So all the data was kind of clustered to the left. So the original distribution from the first time we looked at this question was right skewed. Probability Y we just saw was left skewed. They both had a single peak. The center, meaning the mean that we found earlier in distribution X from a previous problem, that was 2. So we expected, if many students took the quiz, they would on average get 2 questions correct, as opposed to here, they would get 8 questions incorrect. Well, man, doesn't that just make beautiful mathematical sense because there's 10 questions. So the means add up to the 10. That's a good segue to the next thing we're going to learn. I like it. Now the variability on both of them was exactly the same. So wow, if that wasn't a segue. All right. Let's talk about binomial distributions in statistical sampling. Oh my gosh, this is a long lesson, guys. I think it might be more than 3 days. Almost all real-world sampling, such as taking an SRS from a population of interest, is done without replacement. Sampling without replacement leads to a violation of the independence condition, though, in the binomial setting. But when the population is much larger than the sample, the count of successes in an SRS of sample size n has approximately a binomial distribution. So what they're saying is if your sample size is small enough in comparison to your large population, it still behaves approximately appropriate for the distribution. So we have a 10% rule. The 10% rule says that if you are taking a random sample of size n, little lowercase n, from a whole population of capital N, we can use the binomial distribution to model the count of successes in a sample as long as your sample is smaller than 10% of your population. So even though it might not be independent in theory, you can still use the distribution as long as you can prove the 10% rule is okay. And this became a thing simply because they did so many trials and examples and looked at different distributions, and they realized, man, the behavior of the distributions really wasn't affected as long as your sample size and your population had this relationship. So in a survey of 500 US teenagers, 14 to 18 years old, subjects were asked a variety of questions about personal finance. One question asks whether teens had a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. Let X equal the number of teens in a random sample of size 500 who have a debit card. So explain why X can be modeled by a binomial distribution even though the sample was selected without replacement. So what they mean by that is I interviewed a teenager, that means that particular teenager is out. I can't come interview them again. So the next time I go to interview somebody, there's only 499, and the next time there's only 498. Because that's how life works. Like you wouldn't interview the same person over and over again. So this is how we're going to get around the independence thing. So 500 is less than 10% of all the teenagers age 14 to 18. Now, I think that's just one of those like duh moments. Like I don't necessarily know how many exact teenagers are 14 to 18 in the US, but I'm pretty sure that there's more than, 5,000. I think there's more than 5,000 in this town. Okay, so the next question, use a binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. So the probability here would be a binomial distribution with n of 500 and a probability of success of 0.12 that was given to us in the problem. So since they want 50 or less, we are going to use a straight binomial CDF. Remember, it always measures that number to the left on the distribution. And we're going to use trials of 500, a success probability of 0.12, and an x value of 50. Notice we used binomial CDF, so that way it would count and accumulate all of them below. And that came out to 0.0932. I feel like we were supposed to interpret. Oh, it didn't say, so I'm not going to. But if you wanted to interpret that, you could look at it as 9.3%, right? Yeah, we won't bother. This topic is not required for the AP exam. Okay, I hope that didn't mean your ears just plugged up. Some teachers prefer to discuss this topic when presenting p-hat later. You know what? Let's just throw it at you now because I don't know what I'm going to want to do in December. Guys, I might be so crazy by the time December rolls around. Little heads up, it is currently August. We are about to start our first day of school in 2 days, and I'm just trying to get my lessons recorded so I don't have to worry about this later. All right, here goes. As the number of observation n becomes larger, the binomial distribution gets closer and closer to normal. So notice with the same success probability, a sample size of 10 or trial number of 10, 20 trials, 50 trials. The more trials you have, the more normal this is looking. So when n is large, we can actually use a normal probability calculation to approximate the binomial probability. So that's kind of cool because we are going to work a lot with the normal distribution, and we already have a little bit. And that just allows us a little more freedom as to how we calculate probabilities. Now, the only way we can do this is if it's large enough. So how do you know if it's large enough? Well, you're going to use what's called the large counts condition. And again, this was derived from very smart mathematicians back in the day where they just kept doing more and more and more samples to figure out where did it actually behave properly? At what point could we say, you know what, good enough? So the large count condition says that the distribution of x is approximately normal if n times p is greater than or equal to 10, and then n times failure is greater than or equal to 10. So if you can show mathematically, which is pretty easy, it's just a multiplication problem, that this is greater than 10 and this is greater than 10, then you're allowed to use the the normal distribution to approximate any probabilities. Okay? Now, funny how the 10 rule and then this large counts condition also uses 10, so that's kind of nice. Here they just said those same rules in words as opposed to math. So n times p is the expected value or the mean, and then n times 1 minus p is the expected value or the mean of the failures. Okay, so basically expected value of successes has to be bigger than 10, bigger than or equal to 10, and expected value of the failures has to be bigger than or equal to 10. You're going to have at least 10 wins and at least 10 losses. That's what they're saying. So we got those teenagers again. I think you've heard of them. They were asked about personal finance. Yeah, we know. Debit card. 12% of them said they had a debit card. So the first question is justify why we can use the normal distribution now. So if we do n times p, we get 60, which is surely bigger than 10. And then if we do n times q, or n times 1 minus p, the failure, we get 440, which clearly is greater than 10. So we would have to show this on the AP exam that we did n times p and n times 1 minus p, and then show the math. This means we can approximate x with a normal distribution. So our follow-up question, use the normal distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. So using now our normal distribution. So this is where you get a little bit of freedom, huh? In order to create the normal distribution, we have to find the mean and the standard deviation. So we're going to use our n times p to find the mean, and then n times p times 1 minus p square rooted to find the standard deviation. We're going to draw our normal curve. This has to be shown even if you're using your calculator. And we're going to mark on our normal curve what we're interested in. So they want the probability that 50 or fewer. So remember, we're not doing a binomial CDF in this question. We're using the normal distribution to approximate it. I think we already did the binomial PDF. I know I have a goldfish memory, but I kind of distinctly remember doing this as a binomial PDF a minute ago. So of course your book, they first show you what happens when you find the z-score. So they standardized and used the table, but they said, you know what, you could also use your calculator using a normal CDF with standardized data. And if you're Mrs. Abruzzo, you're too lazy for that. So you're going to do a normal CDF with unstandardized data. And either way, you get 8.4% roughly. And on the table, it was pretty close to that. Yep, 8.4%. I don't know that we have it side by side. Okay, back. This is the end of day 2, by the way. Back. Okay, this is what happened when we did binomial CDF. We got 9.3, and we just got 8.4 with the normal distribution. So which one's better? Probably the binomial PDF. I'm sure it wasn't a pure fit with the normal distribution. Notice it just says that we are using it to approximate. Approximated. Thank you, stats, for never being quite accurate, but that's what we do here, right? Okay, let me double check my list here. I'm fairly certain, yes, this is definitely day 3. So we've been talking all about binomial distributions and binomial settings and binomial random variables. Well, there's also something called a geometric random variable. And this would arise when you perform independent trials of the same chance process, record the number of trials it takes to actually get a success. So this is different than binomial because in binomial, you know how many trials you're going to run. And in geometric, you're just going to keep going until you get a win. So it's unknown. This is kind of like that question early on where it said flip over cards, put them back in, and keep flipping until you get an ace. That would be a geometric setting. Yes, of course, your calculator has something, but there's also a formula, so hang with me. The formula is actually not too bad. The number of trials, they're going to call it Y here, it takes to get a success in a geometric setting is called a geometric random variable. The probability distribution of Y is a geometric distribution with probability P of success of any trial. Now notice this time the possible values don't have a 0 in them because you couldn't possibly get a success if you've never conducted a trial. So it starts off at 1 and then it continues on indefinitely until you actually get a success. So here is what's on your formula sheet. I think if we kind of like dissect it a little bit, it's not too bad. This is failure, right? This is losing, and P is winning or success. So you're going to lose every single time until you win. That's what it's saying. So if you won the 10th time, that means you lost the 9th previous times. So like losing 9 times, winning 1 time. That's the geometric formula. And it's actually really simple and kind of common sense if you start thinking about it. Yes, your calculator has some distributions in the distribution menu, which we will see because, you know, I love my calculator. All right, Mr. Lockle, I don't know how you say his name. I'm going to go with Lockle. His class does decide to play the lucky day game. I think this is great. A student will be selected at random from your class and asked to pick a day of the week. So, Sunday to Saturday kind of a thing. Then your teacher will use technology like a random number generator to choose a day of the week as a lucky day. If the student picked the correct day, the class will only have one homework problem. But if the student picked wrong, he's going to move on to the next kid and they're going to repeat the process. So, something to understand, and your book has a very clear explanation about this, and I think in class we should kind of conduct this because I think it's cute. When he moves to the next kid, it starts all over again. So, it's not like, okay, the first kid was wrong, so the next kid knows not to choose Thursday. It's a brand new independent trial each time. So he's going to keep using a number generator every time he goes to a kid. So you'd have to like assign numbers to the days of the week, I suppose, 1 through 7. Anywho, he keeps doing that until he gets up to 10. So the idea is you're hoping to get really lucky and like the first kid gets it right, which means he would only assign one homework problem as opposed to the full 10. If the second kid gets it right, they'll get 2 homework problems and so on all the way up to 10. So this is definitely a geometric distribution, probability distribution, because there's no number of fixed trials because we might stop at 1, we might stop at 2, we might stop at 3, all the way up to 10. So find the probability that the class receives exactly 10 homework problems. So what's the probability that they play this game? And he keeps going until he gets to the 10th kid and then like, oh, bad news, guys. So I had to snip this from the book because there was a typo. I'm telling you guys, there's so many typos. It's crazy. It has a geometric distribution of, now notice we don't have an n because it's geometric. All we have is a p. So the probability of getting it correct is 1 out of 7 because the kid is going to just guess it, right? So the probability of getting exactly 10 on this geometric distribution means that you get it wrong 9 times and you get it right 1 time. Now notice we don't put a 1 because that'd be goofy. I hope y'all caught where the wrong part came from. 6 out of 7 are wrong. 1 out of 7 is correct. So 3.6%. So the next question is find the probability that y will be less than 10. So they're going to do this by hand, and then I'll show you in class on the calculator as well. So the probability that it's exactly 1 or 2 or 3 all the way up to 9, notice they didn't count 10 because it says less than 10, not less than or equal to 10. So the probability of having 1 homework assignment, and then here's 2 homework problems rather. So lose, win, lose, win, ... ellipses work, and then lose 8 times, win on the 9th. And this comes out to 0.7505. So I'm going to show you in your distribution menu where you can get the geometric distribution. And just like with binomial, you'll see that we have to enter them carefully. But now we have to interpret this. So there's a 75% probability that the class will get fewer than 10 homework problems by playing the game. So I guess if it's a matter of do you want to play the game? Like, yeah, because you got a pretty good chance of having less than 10 problems. And if you look at these probabilities individually, obviously, the distribution can be looked at a little bit so you can figure out what's going on. But I mean, why not? If you know you're going to get 10 problems at the worst, then go for it. That's what I say. So, oh, here we go on the calculator. I knew I wouldn't let it get away without a calculator. So we're going to choose for that particular lucky day question, geometric PDF, if they wanted to find a single value. So in this time, they're going to ask for the probability of success and then K, meaning what number we were interested in. So probability of being successful on that lucky day game was 1/7, and then they want to know exactly 10. So boom, there you go. Same answer or a very similar answer. Now for the follow-up question where it said less than 10, remember all these distributions measure from that point to the left. So less than 10 would be 9 and less. So when we enter this time it's a geometric CDF because they want you to accumulate all those numbers to the left and then up to 9, and they want you to stop at the 9. And then looky there, 75%. So I'm going to be honest, guys, while the formula is not terrible, I don't really want to add up a whole bunch of individual probabilities. No, thank you. So I will most definitely be using geometric CDF if the case arises. Now here's a good look at the distribution. This is for the lucky day problem. Part of the probability distribution for the number of picks it takes to match the lucky day. We can't show the entire distribution because the number of trials it takes to get the first success could be a very large number. Now, I didn't look at his lucky day distribution very much. Maybe he doesn't stop at 10. Oh, that's cruel and unusual. Oh my gosh, Mr. Lockle, that's terrible. So if they choose to play the game, they might end up with like a gazillion homework problems if they're super unlucky. Yikes. All right, maybe I don't want to play that game. Okay. Anywho, you notice what happens in this distribution is most definitely right skewed, and that is going to be true for all of your geometric distributions. They're all going to kind of tail off like that. So geez, I keep jumping the gun. Every geometric distribution has this shape. The center, which is the expected value, is 7. If the class played the lucky day game many times, they would receive an average of 7 homework points. Okay, cool. The variability is 6.48. And the class played lucky day game many times. The number of homework problems they receive would typically vary by about 6.5 problems from the mean of 7. Now that's interesting. If you think about it, one distribution to the left of that would be almost 0 problems. So we're assuming they meant 1 problem. And then one deviation to the right of the mean would be, 13, 14 problems. So interesting. Man, I don't know. I'm pretty paranoid. I don't think I could do that. So how'd they come up with those mean and standard deviations, you might be wondering? Well, if you're a bruzo, you probably use technology because you're lazy, but these are pretty easy to calculate. The mean of a geometric distribution is just by finding 1 over p, so the reciprocal of the probability of success. So in Mr. Laughlin's problem, sorry, Lockle, 1 divided by 1 over 7 is 7, which we can talk about why that is, but make sure when you divide fractions on your calculator, you use parentheses. And then the standard deviation is the square root, and notice the square root's just in the numerator of that. So it's the square root of 1 minus p, so failure, divided by the probability of success. So for him, it would have been the square root of 1 minus 1/7 divided by 1/7. Cool beans. All right. Formulas, I believe, are on your formula sheet. I can't imagine those ones wouldn't be, but we'll have to take a look at the formula sheet more closely. Sometimes it's a matter of there's so many formulas and you just got to know where they're at. So we have a local fast food restaurant running that stupid game again. Draw 3, get it free. The computer program then simulates 1 card being drawn from a standard deck. If the chosen card is 3, the customer's order is free. Otherwise, the customer must pay the bill. Let X represent the number of customers it takes to get the first free order on any given day. Calculate and interpret the mean of X. So this is a geometric distribution because we don't know. It could be the first customer, it could be the third customer, it could be the 152nd customer. Like I have no idea when we're finally going to get that winner. So to find the mean, they do the 1 over p formula, which is 13. Notice the parentheses are on that fraction in the denominator. To interpret that, we say if the restaurant runs this promotion on many, many days, the average number of customers that it will take to get the first order free would be about 13. So on any given work day, in general, over the long run, after the 13th customer, you'd be like, boop, we should have had a free meal by now. Again, that's in general over the long run on average, many trials. Calculate and interpret the standard deviation of X. So using that formula, 1 minus square root of 1 minus p over p, careful with your parentheses again, that comes out to 12.49. So if the restaurant runs this lunch promotion on many days, the number of customers it takes to get the first free order would typically vary by 12.5 from the mean of 13. So once again, if the mean is 13 and you take away 12.5, 1 deviation, you're almost down to the first customer basically. And then if you add a deviation to it, now you're at the 25th, 26th customer. Quite the spread. All right, I guess that's all they wanted. All right, cool. Oop, don't show the answers yet. Let's check our understanding. So suppose you roll a pair of fair six-sided dice until you get doubles. Let t equal the number of rolls it takes. Note that the probability of getting doubles on any roll is 6 out of 36, which can reduce to 1/6. So that way we can write our formulas a little nicer. So first they want to show that t is a geometric random variable. And then you want to find the probability of exactly 3 rolls, and then interpret that. And then in the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Really? I didn't know that rule. All right, find the probability that this happens. Fun fact about Monopoly, I guess. And then number 4, calculate the mean and standard deviation at t, interpret these parameters. So pause the video, write down some thoughts. I'm about to show all the answers. All right, show that t is a geometric random variable. So it says die rolls are independent, check. The probability of getting doubles is the same every time. Yeah. We're repeating the random process until we get a success, which is defined as getting doubles. And this is a geometric setting, and t is a geometric random variable with p equals 1/6. So it's very similar to bins, but like we don't have to do the fixed number of trials because that's not geometric. All we have to show is that there's some independence, and that we're repeating it until we get a success, and then define what that success probability is. Oh, and that the probability is the same on each roll. Okay, second question, t equal to 3. Now they did it with the formula. So if you win on your third time, that means you lost, and then you won. So lost, won. That's what you have here on the math. So you lose 5 out of 6 times, 5 out of 6 times, and then 1 out of 6 win. You could have done geometric PDF with 1/6 as your probability of success and your, I think they call it K value. I'm not sure what they call it on your calculator, of 3. X maybe? X. So to interpret that, there's 11.57% probability that you will get the first set of doubles on your third roll. So then for the Monopoly question, you would get out of jail if you ran doubles on the first or second or third roll. So you could either find the probability of 1 and then 2 and then 3 and add them together, or if you're lazy like me, you could do a geometric CDF and do 3 down. So 3 would be your X value. So either way, this is probability of getting it on your first roll, your second roll, your third roll, and adding them together, you get a 42.1% probability of getting doubles within the first 3 rolls. So you almost have that's a pretty good probability of getting out of jail. Man, I did not know that rule in Monopoly. I feel like someone's cheated me over the years. Okay, so the expected value for this distribution, or the mean, is 1/p, so that's 6. If this random process was repeated many times, the average number of rolls it would take to get doubles is about 6. And then the standard deviation is 5.477. Have you noticed, guys, that the mean and the standard deviation are pretty close together? Yeah, I think that's a thing, man. If the random process is repeated many times, the number of rolls it will take to get doubles will typically vary by about 5.477 rolls from the mean of 6 rolls. Okay. And that's it. My goodness, that was a long lesson. All right, so again, it's supposedly we're doing that in 3 days. I think it depends on how much we want to have fun with the calculator. And actually doing it straight with the calculator, of course, would save us time, but I think there's value in finding the formulas. So, don't be so married to your calculator where like you can't use the formulas, because remember, the formulas are what you actually are given on the test. What if your calculator died in the middle of the test? I mean, that would be god awful. I hope that doesn't happen. And really, the whole point of that test is not how good of a number cruncher are you, but can you interpret it? All right, that's all I got for you. That should be the end of semester 1. I feel like celebrating. Bye, everybody.